We are going to be spending quite a bit of time now talking about optical glass or glass. Now, when I say glass in an optical system, it simply means the material components are made of. So yes, sometimes your components may be made of plastics, which are obviously technically not glass, sometimes possibly crystalline materials, sometimes even liquids or gases. But for now, what I want to talk about or concentrate on is what we call typical optical glass. Understanding the definition of glass, and in particular how glass behaves in an optical system, is key in designing an effective and efficient optical system. You need to be able to use the right optical materials, taking into account what the environment your system will be used in, whether it's a one-of-a-kind system or something designed to be mass-produced. All of these will affect how to select the proper optical materials to use in your particular design. Now, when we go back to Snell's law, so far we've been simply applying paraxial ray tracing, and I've just, in a couple of examples, given you an index of refraction value. But if we look at Snell's law, remember there were two parameters of interest, the index of refraction and the angle of incidence at the point of intersection on a surface. We've spent quite a bit of time looking at calculating the angle of incidence and the angle of refraction. So now let's talk a little bit about index of refraction, because you absolutely must understand not only the index of refraction, but other important properties of glass in order to do quality optical design. So what exactly is a glass? And we might start with a dictionary. And here is from Google, what is glass? A hard, brittle substance, typically transparent or translucent, made by fusing sand with soda, lime, and sometimes other ingredients and cooling it rapidly. It's used to make windows, drinking containers, and other articles. And fundamentally, a lot of that is correct when we talk about our optical glasses as well. But what we have to talk about is that basically a glass is a material that undergoes a glass transition, and for those of you who studied English in the past, using a word as part of its definition is typically not accepted. But what this means is we have a combination of materials that, yes, starts by fusing or melting together sand and soda, lime, other ingredients, but it has a set of physical properties that vary with temperature. At lower temperatures, it's hard and brittle and easily breakable. At higher temperatures, it is softer and more pliable, somewhat plastic-like, if you will. Now, when we talk about optical glass as used in optical design, we're talking about a compound of inorganic materials. They are typically based on fused silica, so silica is the primary ingredient in optical glass, but it's mixed with soda lime, boron, flint, other materials. These are melted together and blended at a relatively high temperature, a temperature where all the materials are liquid, if you will, and then cooled through a very controlled process. It is the ratio and the combination of these different elements that determine how the glass behaves in an optical system. Typically, when you're designing an optical system, you're going to have multiple elements, and those multiple elements will be made of at least two different glasses, optical materials, if not more. Now, just as an aside, you may have heard this. I don't want to call it an internet tale because I remember this from when I was like in 5th or 6th grade, and it absolutely fascinated me. The concept that glass is a fluid. No, it is not. Glass does not typically crystallize. As a matter of fact, crystallization in glasses creates spot defects in the material, and they're not wanted, but glass is not fluid. So despite what you might have heard, no, the church windows in medieval cathedrals are not thicker at the base because the glass has flowed over the centuries. It's simply a result of the manufacturing processes available at that time. And of course, optically, the important part or property of glass is that it can reflect, refract, or transmit light. There are two typical characterizations of glass or definitions of materials. They're referred to as crowns or flints. Crowns are the most common types of optical glasses. The original window glass, if you will, was a crown material. They tend to have a lower refractive index range, from about 1.5 to about 1.65, but doesn't mean they can't be outside that range. They also tend to have what's referred to as an Abbe number that is higher, say in the range of 50 to 85. The higher the Abbe number, the lower the dispersion, which is a measure of how index changes with wavelength, and we'll be talking about dispersion very shortly. In addition to the silica, crown materials typically have an alkali lime component, phosphorus, potassium, zinc, barium, or lanthanum or lead oxides. Additionally, lead over the last 20 years or so has been phased out of a lot of optical manufacture, but not completely. And it again is these different materials and different combinations that allow components that behave differently, allowing us to create better optical designs. The other classification of optical glasses are what are referred to as flints, and historically these were the original lead crystals. Okay, they were made originally by mixing flint material, which was basically lead oxide, with the silicon dioxide to create these very, very transparent windows. Again, the original application. Nowadays, you're more likely to see titanium or zirconium oxides due to environmental concerns. Lead is not good in the environment. Flint materials tend to have a higher dispersion, so a lower Abbe number, typically lower than 50, but let's say lower than about 55, and we'll give some more exact definitions shortly. And they also tend to have higher refractive indices than the crown materials, although their indices can be as low as 1.5. Typically they're 1.6 to 2 in index of refraction at the 587 nanometer wavelength. These flint materials typically are very highly transparent in the visible, and they tend to be highly absorbing in the ultraviolet region. And again, when we talk about glass, when we're doing optical design, we don't necessarily mean glass as defined in terms of physics or the dictionary. Other materials you may need to include in your optical design could be gases. Typically, we think of our optical systems being in air, but there may be reasons or portions of your optical system that may be in some other inert material, nitrogen, argon, others that have other refractive properties than air, so you'll need to include that in your system design. Also, a lot of systems these days do have plastic components, acrylics, polycarbonate, polystyrene, etc., etc. Liquids are also common in optical systems. There are systems that do indeed have liquid lens elements, but also we may have systems that are submerged in water, seawater. We may have refractive index matching fluids, for example, in a microscope system. We may have liquid core fibers. Again, perfectly valid optical materials. And although we talk about glass in terms of physics not crystallizing, there are crystalline materials such as calcite, quartz, zinc sulfide, and selenide, typically more commonly used in the infrared. KRS-5 or other salts can also be used as optical materials. So this is a little bit about what is a glass, and in the next several lectures what we'll talk about is what are some of the properties of glasses. Thank you.